Okay, we are now beginning lesson 6.2. This is tutorial number 1 for 6.2. It corresponds pages 563 to 574 in our book, and then also 577 to 583. Okay, in the last lesson we learned that rate, for this equation, A decomposing to B, just one reactant, the rate could be written as the opposite of the change in the concentration of A over the change in time. If we knew that, we could calculate the average rate, and we learned also how to write that as a rate law. A rate law being rate equals a constant times the concentration of A to a power. And we called this power the order of the reaction. Now we're going, in this case we're evaluating rate and concentration. How concentration, when we looked at rate laws, changes in concentration affected rate. Now we're going to look at rate and time and how those two things are related, or how we can evaluate time to determine rate. So, for a first order reaction, this N is going to be a 1. So we'll take a red pen and just make that a 1. And what we can say here, well, we'll make it a 1 over here too. Okay, 1. So now we have the opposite of the change in concentration of A over the change in time equals K times the concentration of A to the first power. Now, using calculus, which we're not going to actually use here, but it is used to create this what we're going to call the integrated rate law. And you don't have to write anything down, we'll write it down in a second. And if you want to see how this integrated rate law is derived, I'll post something on Vision and you can take a look at it. But before calculus is used, there's a little rearrangement that goes on. You have, from this equation, we can move the minus sign to this side, and then we can say the change in the concentration of A over and the change in T equals minus the change in A times K, and then if we multiply both sides by delta T and we divide both sides by K, we end up with something new, which is delta A over K equals the opposite of the change in A, delta T. And now calculus can be used here to integrate this, and after you integrate this thing that I just wrote in purple, what you get is this equation here. And so the natural log of the concentration of A at a certain time T divided by, and this is actually, this is the natural log of this. Just like I had to rewrite it because when I put things from PowerPoint into my video, the subscripts get all kerflooey. We'll just put parentheses here. So the natural log of the concentration of A at a certain time divided by the concentration of A at the start, equals minus K times time. So A with the subscript of 0, which is what you have on your paper, I think it's the second thing, is the initial concentration of A. It's the concentration that you start with, so you want to write that down. And A subscript T is the concentration of A at some time T during the course of the reaction. So you have two concentrations, one when it starts, that's this one, and one when you're measuring it, some time has passed. Okay, so we're working with natural logs here. And if you need a review of a logarithm is just an exponent. If you need a review of logarithms, I will post on Vision a short Khan Academy video, and also I will post two videos, both from Khan Academy, one a short review on logs and one a short review on how to calculate the natural log with your calculator. That one's about 3 minutes. So if you want to stop now and watch those, you can, but a logarithm, whether it's the ln, the natural log, or log like log, is just an exponent. And in this case, When we use the natural log, it's e equal to something. Let's say this was equal to 7. I put my 7 in the wrong spot. So if e, what all this is saying is that e to the x power would equal 7. And you're trying to find out what power that is. A logarithm is a shortcut for exponents. It's just like multiplication is a shortcut for addition. When we do 4 times 3, we can do 4 plus 4 plus 4. That's addition, equals 12. Or 4 times 3 gives you 12. It's a shortcut. So logarithms are shortcuts. If you need a review, watch the 2 videos on vision, or you can ask me in class. But we're down here now. Okay, we had an equation on the previous page that looked like this. Sorry about my subscripts. It looked like the natural log of A at a certain time divided by your initial concentration of A equaled minus K times T. And using rules of logarithms, we can manipulate this. If you have a log of a fraction, it's the log of the first thing minus the log of the second thing equals minus KT. And we can manipulate this using algebra if we add the natural log of A to the 0 to both sides to come up with this equation. So this equation that I am circling is just an algebraic manipulation of this one. And this is the one you want to write down where it says first order. Well, actually, this is what you want to write down for integrated rate law for first ordered process. This is our integrated rate law for a first order process. And the rate law for the first order process, which we'll write in blue, would be rate equals K times the concentration of A to the first power. Okay? Now what's important about this thing that you just wrote down is its form. If you look at it carefully, it's in the form of y equals mx plus b, which, as you know from algebra, is the equation for a line. So when we have a first order process, if we can write the data that we have for that, or if we can write it in the form of the integrated rate law, our y values will be the log of concentration at a certain time. Our x values are going to be time, so we're going to be plotting time versus the natural log of the concentration. The slope is going to be the opposite of k, and the y-intercept will be the natural log of the initial concentration. So we're going to use this, okay? So if we have concentration data for A, and we have time data, and if we plot the log of our the natural log of our concentration data versus time, so that would be a third column here, natural log of A, and we get a straight line like this, then we'll know that's a first order process, because the plot of the natural log of the concentration versus time, if it's a first order reaction, will give us a straight line. And we'll be able to calculate the y-intercept, and that will tell us we'll be able to figure out from that the initial concentration, and we'll be able to figure out k from the slope of the line. So let's practice doing that. And make sure on your paper you have written down that y for a first order process is equal to the log of the concentration at a certain time, and that the slope is equal to minus k, and that the y-intercept, b, is equal to the log of the natural log of the initial concentration. Okay, so now to practice this, we're going to think of a reaction where, and this just is really annoying, where methyl isonitrile, CH3NC, is converted or decomposes and becomes acetonitrile, CH3CN. The C in the end, these bonds are broken and they flip. Okay. So we're going to think about this process where we actually saw this reaction before in the previous class, where these bonds are being broken and switching. Okay, so for this reaction, the concentration, and by the concentration was able to is analogous to the pressure, because the pressure is measuring how many molecules are bouncing around. So for gases, you can use pressure as an analogy for concentration. Concentration was plotted versus time, and you see this is not a straight line. So therefore, the data was replotted. The natural log of the pressure was calculated, and that was plotted versus time, and that is a straight line. So that tells us that this is a first order process. It's a straight line that fits this equation of a line. This is y equals mx plus b. Our y is the natural log of pressure, which is standing in for concentration. That is here on the y-axis. Our x is time. That's our x-axis. This is a straight line, so that tells us it fits this equation, which means it must then therefore be a first-order process. If we were to calculate the slope, it would be minus the slope would be k. K is the negative of the slope, and they did calculate that for us. And this is supposed to be 5.1 times 10 to the negative fifth. So here we have some data for the reaction. The decomposition of hydrogen peroxide, H2O2, decomposes into water plus oxygen. Data has been collected for the concentration of hydrogen peroxide. You see it decreases as the reaction goes on because it's decomposing. It's over time. These data points, yx, this is y, were calculated. And you end up with a graph like this. Now you can see this is not a straight line. So therefore, we have to do something else to figure out what order it is. If it was a straight line when you calculated concentration, when you graphed concentration versus time, that would be a zero order reaction. We'll talk about that in several slides. So now more work is needed. We must graph the natural log of the concentration of H2O2 and see if that gives us a straight line. Okay, so here I'm going to calculate, using my calculator, the natural log of H2O2. And we'll practice this in class, so I'll go over it again in class, but in order to calculate the natural log, you hit ln on the left side of your calculator, and then type in the number. So here our first one is 0.020, 0.02, close parentheses, hit enter, and the natural log of this is minus 3.91. Okay, I'm going to do the next one. I hit ln on the left side, I type in 0.0118, I hit close parentheses, and I hit enter, and that is minus 4.43. Okay, so I'm going to pause and do the rest. Okay, so I have calculated the natural log of, of H2O2 for each of these numbers. The natural log of 0.02 is negative 3.91. The natural log of 0.0118 is minus 4.43, and we will practice doing that in class. Now I'm going to use my graphing calculator to graph this as the y-axis and this as the x-axis. And we'll practice plugging this in our graphing calculator in class. You don't need to do that right now. Okay, and you can see in green that the graph of what did I just tell you? The graph of the y, hold on a second. Okay, so the graph in green, to be clear, this graph right here, this straight line, is the graph of the natural log of H2O2 on the y-axis versus time. And when we graphed that, we got a straight line. We did not get a straight line when we graphed the concentration versus time. That was on the previous slide. But when we graphed the natural log of H2O2 versus time, we got a straight line. That tells us that this is a first-order reaction. So if we consider a reaction like the one on the previous page, hydrogen peroxide decomposes into water plus 1/2 of an oxygen molecule. If we take data of that, of the concentration of our reactant versus time, and we plot it, and that is a straight line, then it is a first-order reaction. So write this down underneath on the first page at the bottom. If the graph of the natural log of A, the concentration of a reactant, versus time is a straight line, then it is first order in that reactant. Okay, this particular reaction has only one reactant, so it's a first order reaction. Write this down. The integrated rate law is the natural log of, in this case, the reactant. This could also be the natural log of A, whatever your thing is, equals minus K times T plus the natural log of A0. Write this down. The slope of the line is equal to the opposite of K. Which means that K can be discovered if you find the slope and you take the opposite of it, that will be K. Your y-intercept, write this down, is equal to the natural log of A0, which means you can find your initial concentration from your y-intercept. On our previous slide, the y-intercept was minus 3.91, so that is equal to the natural log of A to the 0. If we take the inverse of this, we will find out the y-intercept. So on your calculator, if you take, and the inverse of this would be E, oopsies, do it in red, E to minus 3.91 will equal the initial concentration. So on your calculator, if you hit second and ln, that gives you e to the x, and in the little flashing box you type minus 3.91 and hit enter, you will get the y-intercept, which doesn't look right to me. Nope, it is right. So if you do that, e to minus 3.91 is equal to the initial concentration, which is 0.020 moles per liter. For the entrance quiz, I want you to recognize that if you have a straight line when you graph the log concentration versus time, that means that it is first order in that reactant. This is the integrated rate law, which is actually on your equation sheet for the AP exam, and we'll talk about that in class. This is the end of this video. Next one we'll start talking about second order processes.